Alright, so here we're starting on circular motion. It's really not too much different from projectile motion. We still have sort of, motion in two directions rather than just in one like we had at the beginning of the year whenever we were talking about velocity, distance, displacement, and things like that. So we're going to start looking at circular motion. We've got some definitions to begin with. We've got rotation and revolution. Now, these are two different things, and so let's just talk about the differences. Rotation is when an object is spinning around an internal axis. One example is a spinning top. All of the parts of the top spin around a point that's inside of the top. Okay, so they all spin around that center point. One example of this for you would be if you're standing there and you hold your arms out and you spin around in a circle. That's rotation, because all of the points of you are moving around sort of the center of your body. Another example would be the Earth, the way it spins. When it spins around its axis, that is rotation. If you go to revolution, that's an object that's spinning around an external axis, so it's moving around it. The example here is the Earth moving around the Sun. It's moving around a point that is not at its center. The center of its circular motion that it makes is actually at the Sun. So that's really the only difference between rotation and revolution, is whether the axis is inside or outside of the object. The axis is just sort of the point that it spins along. A couple more definitions. Tangential speed and rotational speed. Now, tangential speed is pretty much the same definition of speed as we know it already, which is the distance covered per unit of time. The difference here when we're looking at circular motion is that the distance that's covered is the circumference of the circular path that the object is going along. So we have to multiply 2 times pi times r, which is the radius of the circular path it's moving along, in order to figure out the distance. We divide that by the time it takes for the object to go around the circle one time. This type of speed, tangential speed, is expressed in meters per second, just like the speed that we're used to. The other type of speed we're going to talk about in circular motion is rotational speed. Rotational speed isn't a distance per unit of time. Instead, it counts the number of rotations in a given time. So the one that we're going to be looking at is called RPMs, which is rotations per minute. Basically, you start your stopwatch and you count how many times the object goes around the circle, how many laps it makes in 1 minute. And that's your number of RPMs, or your rotational speed. Now, an interesting thing to think about is if you're standing in the exact center of, the example here is a recording disc, but you can think of a merry-go-round or something like that. You're standing in the very center of it. Do you have any tangential speed, and do you have any rotational speed? Okay, well, you don't have any tangential speed, but you do have rotational speed, because you'd still be spinning in a circle, but you wouldn't really be covering any distance. Rotational speed stays the same no matter where you are on the disk or on the object that is rotating. So if you stand on the outside of a merry-go-round or you stand on the inside of a merry-go-round, it doesn't make a difference. You have the same rotational speed. It's the same no matter where you're at. The tangential speed, though, it does change. It actually gets greater as you move farther away from the center of your object that's rotating. So in this case, from the center of the disk, or the center of the merry-go-round. Your tangential speed gets greater as you move farther away from the center. So here's a centripetal force demonstration. So if you want to check this out, just go to the PowerPoint and click on the link. It's going to show you some cool stuff, and it's going to point out the direction of the force that keeps an object moving in a circular path. Okay, it's really neat. It's a good demonstration, so check it out. So the name of the force that you hopefully just checked out in the link from the previous slide is called a centripetal force, which means it's a center-seeking force. It makes objects move in a circular path. It accelerates them towards the center of whatever rotation they're going around. Now, the way you calculate centripetal force really is mass times centripetal acceleration, like this just says. Okay, m times ac. AC is the acceleration. The way you find AC is you take the velocity and you square it, and you divide it by r. So the full formula for the centripetal force is mass times velocity squared divided by r. Now that velocity that you're squaring, that's the tangential speed, not the rotational speed. If you use the rotational speed there, you're going to mess everything up. So tangential speed every time. Now if you notice here, if you double the mass of the object, it takes twice the force. Okay, that's the same as we looked at before. Now, how about if your radius gets bigger and bigger? That means that your force is smaller and smaller. How about if you go faster and faster? If you move faster, then the force is greater. Think about the way that you were spinning the little rubber stopper in the experiment that we did. Okay, if you had more weight on it, more force, then you had to spin it faster. Now, another force that you may have heard of is called the centrifugal force. Centrifugal. So it's really what that means is center fleeing force. And I gotta tell you this right now, it's not a real force. Okay? There is no force that pushes outward whenever something is going in a circle. The only force that's acting is that centripetal force. The centrifugal force is just one that we think we feel, and what you're really feeling is inertia. It's your body trying to keep going in a straight line, even though the object that you're in, like if you're on a little cart on one of those circular rides at the fair, it's the thing that's keeping you going in a circle. Your body wants to keep going in a straight line, and so you feel that as a force being pushed out, because you get pushed against the outside wall. That's what it feels like, but there isn't really any force pushing you against the wall. Rather, the wall is pushing inward to keep you moving in a circular path. One really neat thing about this is that in space we can simulate gravity for astronauts. Okay, if we have the astronauts in a spinning sort of pod or something like that, if it's spinning fast enough, then the centripetal force that's holding them in will make it feel just like they have the same gravity as they do on Earth. That's really interesting, and hopefully we'll be able to show you an example of it in class. Or if you want to check it out, you can check it out on the internet. Look up simulated gravity, and there will be some interesting things on there. They'll show you these circular objects that look almost like a hamster wheel, except for an astronaut. And that's one of the ways that they think they might have to go about creating space stations whenever they actually are taking these long distance trips into space, because there's a lot of effects that really are harmful to humans when you don't have gravity, because we're kind of made for gravity. The other things you need to know for circular motion, it's called torque. Torque is what produces a circular motion, and it's basically a perpendicular force against what we call the lever arm. The lever arm is the distance from the fulcrum out to where we're pushing on it. So if you think of the example of a wrench and you're using it to turn a bolt, well, the fulcrum there is where you're connected to the bolt, and the lever arm is the distance from there to the end of the wrench where you're holding it. So if you push straight down on the wrench, sort of perpendicular to it, then that's when you get the maximum torque. Torque is what creates a circular motion. If you have balanced torques, like if two people are sitting on a seesaw and it's not moving, that's called a balanced torque. It means that the force times the length of the lever arm on the left side has to be equal to the force times the length of the lever arm on the right side. So we're going to look at some problems that have torques in them, so you'll have some practice with it. But basically, if you think of the idea of a seesaw and you have a person on each side, they don't have to be the same weight in order for the seesaw to balance. If one person is really heavy on the left side, then you could change the distance on the right side to compensate for that. You wouldn't have to put more weight on it. And we'll take a look at that and see how that does it. We'll even do a lab on it. Now, a new term here that we haven't talked about before and you may not have seen before is called static equilibrium. And it just means that the object is not rotating, in this case, that the net torque acting on the object is zero. When I say net torque, you should think back to when we were talking about net forces. When we talked about net force, we talked about adding up all of the forces that are acting on an object. This is the same idea. We talk about all of the torques that are acting on an object. So in this picture, we have the torque of the guy on the right, that is a clockwise torque being exerted on the seesaw, and then we have the torque from the person on the left, that is a counterclockwise torque. So as long as they cancel each other out, then the net torque is zero, and it's exactly the same as if no one was sitting on the seesaw. If the net torque is zero, then it's not going to rotate. So that would be static equilibrium. And that's pretty much it for the notes on this. We're going to look at some labs. We're going to try and look at some cool demonstrations. But pretty much that's all of the notes for this unit. And if you can get this stuff down, then we are in the good.